Good evening. My name is Yasir Abdulkareem Jamal. Today I will present one of the most important problems in computer science. It is the 0-1 knapsack problem and how it can be solved by the two different approaches of dynamic programming technique. So the contents of our presentation include the knapsack problem. We will get to know its types and its statement, and we will concentrate on the 0-1 knapsack problem, and we will see how it can be solved by the dynamic programming technique. We will recognize on the dynamic programming in the next part. We will get to know its definition, its history, and the main idea of this technique. After that, we will explain the two approaches of the dynamic programming that we have used to solve the 0-1 knapsack problem. It is the bottom up and top down. We will see how they work and the concept of each approach, and we will explain their algorithms practically. After that, we will explain the results we have gotten from our experiment we have made to test the performance of these two approaches for solving the 0-1 knapsack problem. In the last part, we will summarize the most important points we have discussed in our presentation. So in the beginning, we have to know the statement of the knapsack problem. The statement says that selection of some items, each item with the profit and weight values, to be packed into one or more knapsacks with capacity. The item, profit, weight, as well as the capacity of the knapsack are all assumed to be positive integers. This statement is general for all knapsack problem. In our cases, in 0-1 knapsack problem, we have some items. Each item has a value and a weight, and we have one knapsack with fixed capacity. All these values are positive integer. The knapsack problem is said to be an optimization problem. The optimization problem is a problem of finding the best solution from all feasible solution. Also, the knapsack problem is a non-deterministic polynomial complete problem. That means it's very hard to achieve the optimal solution. Also, the knapsack problem is hard problem due to the computational complexity. Also, we have to say that the knapsack problem has many applications in our real life. It is used it is applied in education, in administrations, in investment, in the finance, and in selection of projects, and so on. So there are many types of knapsack problem. Here we will review some of these types that is related to the 0-1 knapsack problems. The first one is the 0-1 knapsack problem itself. As we explained in the beginning, in the 0-1 knapsack problem, we have some items. Every item has value and weight. 0 and 1, that means that every item is indivisible. That means we cannot break down this item, so every item either is taken or is left. This is the main difference between the 0-1 knapsack problem and the fractional knapsack problem. In fractional knapsack problem, the item, every item can be divisible. We can take a part of the every item. Also, we have unbounded knapsack problem, and we have bounded knapsack problem. In bounded knapsack problem, every item has unlimitation quantity. That means we can get a number, unlimitation number of every item, and we can take it and pack it up in the knapsack. The bounded knapsack problem, there is a limitation, a quantity of every item we can take. This is the main difference between the unbounded and bounded knapsack problem. But we have to point after the important thing that the 0-1 knapsack problem is considered at the root of all these types of the knapsack problem, and it is considered as the classical problem for the knapsack problem. Okay, here is the formal description of the 0-1 knapsack problem. We have a group of items. Every item has value and weight, and our goal is to select some items with maximum value of this item without exceeding the capacity of the knapsack, and with condition of every item is either taken or left. Many algorithms and techniques have tried to solve the 0-1 knapsack problem. One of these techniques is dynamic programming. Dynamic programming is a technique for solving the optimization problems that has some properties. I want to highlight about some properties. Some properties here is the optimal substructure and the overlapping subproblem. We will discuss and explain these two properties in the next slides. Dynamic programming was invented by the American mathematician Richard Bellman in the 50s of the last century. He was the inventor of this technique. Programming doesn't mean coding in programming, but the programming word means planning. The dynamic programming works on a principle of optimality. This principle was defined by the Richard Bellman, and this principle says that the optimal solution of the optimization of problem is composed of the optimization of the optimal solutions to its subproblems. Here we can explain the main idea of the dynamic programming, the concept of dynamic programming. The main idea of dynamic programming is to divide the main problem into subproblems, and every subproblem will be solved once, and the optimal solution of this subproblem will be stored in the memory. So in this case we will avoid the repeated computation for the subproblems by using the memory to save the optimal solution of the subproblem. As we said in the definition in the of the dynamic programming solves the problems that has two properties. The first one is optimal substructure, and the second one is overlapping sub-problems. In the first property, we can explain it by this example. This example, when I'm pointing now, this is the main problem. It's broken down into three sub-problems. The first sub-problem will be solved. Okay, when it will be solved, the optimal solution for this first sub-problem will be used to solve the second sub-problem. So the second sub-problem will use the optimal solution for the first sub-problem. When we reach to the third sub-problem, the third sub-problem will use the optimal solution for the second sub-problem and the first sub-problem to solve the third sub-problem. The overlapping sub-problem, we can explain it by this example of Fibonacci. As we see here, here is Fibonacci 1 and Fibonacci 1 in every side. That means the sub-problem will be repeated. This is called overlapping sub-problem. When there is many overlapping sub-problem in the optimization problem, so the dynamic programming will be present to solve like these problems. Okay. The first approach we have used to solve the 0-1 knapsack problem, it is the bottom-up approach. The bottom-up approach solve in the beginning the problem. It will be broken down into sub-problem, and the smaller sub-problem will be solved in the beginning, and we will solve the sub-problem larger and larger until we reach to the optimal solution for the problem as whole. Also, I have to say that every sub-problem will be solved once. In bottom-up approach, the bottom-up approach, we solve all the sub-problem. This is one of the differences between the bottom-up approach and the top-down approach, as we see in the next slides. Bottom-up approach is considered as the classic dynamic programming approach. Here is the function of the bottom-up approach we have used to solve the 0-1 knapsack problem. But before we execute this function, we have to create the two-dimensional array to save the result of the sub-problem in the cells of array to avoid the repeated computation for the same sub-problems. As we see here, we have three cases. If there is no item or the capacity is 0, then the optimal solution is 0. Else, here we have two cases. If the weight of the current item is less or equal the capacity, then the optimal solution for the current sub-problem will be either one of these values. The first part represents if the item is included, and the second part represents if the item is not included. We will take the maximum of these maximum of these two values. Else, the third case, if the weight of the current item is greater than the current capacity, that means the current item is excluded, not included. This is a practical example of the bottom-up approach. This is the two-dimension array. The first row will be the cells of the first row will be 0, and all the cells of the first column will be 0. As this is the first case, or the base case. Okay. Here, by this formula, we will fill all the cells of this array. Okay, until we reach to the last cell in the bottom in the right. This is value, the 9 value represent the optimal solution for the main problem. We have to refer to a most important thing here. As we see here, every cell that represents the optimal solution for certain sub-problem. For example, if the capacity 1, and we have we use 2 items, 1 and 2, so the optimal solution for this sub-problem equal to 4. By the way, in this row we will use the first item. In the second row we will use the 1 and 2 item. In the last row, we will use the third and second and first item. For example, in this cell, this cell represents the optimal solution of the sub-problem for capacity 2, and when using the first and 2 and first and second and third item. Okay. Here is the function for finding the items we have selected in our optimal solution. The idea of this function is to compare the current value of the item with the upper value of the sub-problem. Okay, let's explain this function by this example. Here we will begin from the last cell. From here we will compare the value of this optimal solution with the upper value. If it is equal, that means the item is excluded, not included in our optimal solution. That means the third item is not included in our optimal solution. Okay. The second step, we are here. We will compare the 9 with the 4. It is not equal. That means the item 2 is included. After the item is included, we will go up to the upper row, and we will subtract the weight, the capacity 3 from the weight of the item 2, as we see here. 3 minus 2 equal 1. So we will go in the upper row in the first column that represent one weight. Okay, in the third also we will compare the value of this item with the value of this cancel of the optimal solution of this sub problem with the upper value. It is not equal. That means the first item is included in our optimal solution. We will subtract 1 minus 1. 1 represent the capacity, and 1 the weight of the item 1. It is 0. The result is 0. That means as we see in the function, if the condition of stopping when the number of item or the capacity is 0, we reach to the 0. That means we have finished. Okay. Before we move on to the next approach, we have to know in a brief the divide and conquer algorithm and how it works. Divide and conquer, like dynamic programming, it divides the main problem into sub-problems, and it will solve each sub-problem. And after that, it will combine all the optimal solution for the sub-problems to solve the optimal solution for the main problem as whole. The disadvantage of this algorithm, it will compute the repeated same sub-problem, as we see here in this figure. Here we have sub-problem, and in the right side we have the same sub-problem. In divide and conquer will solve this sub-problem and will solve the same sub-problem. That means more work and more time. So the time complexity of the divide and conquer will be exponential. That means it's too much to solve the 0-1 knapsack problem. Is there better? Yes. The top-down approach or memorization, we can consider it as the development of the divide and conquer. Top-down approach, like hybrid between the divide and conquer and the dynamic programming. Top-down approach use recursion. Recursion that means the function call itself, and using the two-dimension array to store the optimal solution for the sub-problem. solution of the sub-problem, it will be solved. Here is the function of that we have used to solve the 0-1 knapsack problem. Here we have some cases. The first case, when the number of items is 0 or the capacity is 0, then the optimal solution for the sub-problem will be 0. In the second case, this case represents when the sub-problem is solved. So in the beginning, the top-down approach will check if the current sub-problem is solved previously. If the current sub-problem is solved previously, it will bring the optimal solution for the current sub-problem without any more computation. Okay, if the sub-problem is not solved, so the top-down approach function, it will solve the sub-problem, and it will save the optimal solution for the sub-problem in the data structure. Here we have two cases. If the weight of the current item less or equal the capacity, then we will take the maximum of two values. The first values if the item is included, and the second value if the item is excluded. The last case, if the weight of the current item is greater than the capacity, then that means the item is excluded, not included in the optimal solution for the current sub-problem. This tree represents the recursion tree. This is as example of the how the top-down approach works. Top-down approach also uses two-dimension array. Okay, in the beginning, before we execute the function of the top-down approach, we have to create the two-dimension array, and we will fill all the cells for this array with -1. And as the bottom up, every cell of this two-dimension array represent the optimal solution of a certain sub-problem. As we notice here, some cells are not computed. It is remain as -1. This is the main difference between the bottom up and the top down. In the bottom up, solve all the sub problems, but in top down case, top down or memoization approach will compute just some of the sub problem that it is needed. Also, until we reach to the last cell, this cell represents the optimal solution for the main as a whole. Here also we have to point out to this red colored. Here is the overlapping. When this sub-problem is computed, so in the here it is not needed to compute again, because the value value of capacity 6 and with 2 items capacity 6. So here this equal 9, this 9. So the repetition of more computation is avoided in the two approaches, in top down and in bottom up. Okay, the two approaches have time complexity O, big O of n multiple C, the n that represent the number of items, and the C represent the capacity of the knapsack. And we have refers to something that, as we see here, this time complexity, we can name it polynomial time. Because of we are using the memory, then the auxiliary space equal big O of the number of items multiple the capacity of the knapsack. In general, the dynamic programming is optimization technique. We will give example as we have seen. Divide and conquer, solve the 0-1 knapsack in exponential complexity time. The dynamic programming is solved the 0-1 knapsack problem in polynomial time. That's mean there is enhancement in the execution time. Okay, let's move to the experiment we have made to test the performance of the two approaches. We have used the Python version 3 to write the code, and the experiment has tested on the laptop with the features Core i7 CPU and with 8 GB RAM. Also, we have used the function that generated 10 groups of items from 100 to 1000 items with random numbers. Okay, and when we make our experiment, all of this testing with the fixed capacity, the capacity was 1000. Okay, before we make this experiment, we have tested the function of the top down and the bottom up to assure that it is correct, they work correctly. So when we make our experiment, every group of items, for example the 100, we run every approach 50 times, and we calculate the average times of average time of the 50 times. We have gotten these results when we make testing for 100 items and 200 and 300 until we reach to the 1000 items. We have gotten this time as we see here in this graph. conclude when the number of items become increasing, the tabulation approach with the blue become overperforming and take advantage of the memoization, as this is the difference of the time when the number of item become increasing. We can conclude in our experiment, we can get a result that the two approaches gave the optimal result in all cases when we are testing from 100 to the 1000 item. All the two approaches give the optimal result, optimal solution, but there is the difference the difference of the time between the two approaches begin appearing with overperforming to the bottom-up approach. The last part, we can summarize the most important in our presentation. We explained the knapsack problem. We recognized the types, or the most important types of the knapsack problem. We have known the statement. The general statement of the knapsack problem. We have seen the formal description of the 0-1 knapsack problem. Also, we explained the dynamic programming, the main idea of the dynamic programming, and we have known the properties of the optimization problem that must be available to use the dynamic programming to solve these optimization problems. Also, we explain the two different approaches of dynamic programming and how they solve the 0-1 knapsack problem. We have recognized their algorithms, and we have seen the practical example of the algorithms, and finally we discussed the result we have gotten from the experiment we have made to test the performance of the two approaches to solve the 0-1 knapsack problem, and we have seen how the tabulation approach, or bottom-down approach, how took advantage when the number of items begin increasing. Okay, thank you for listening.